if you're in the process of learning vectors, then what you'll notice is that some of the topics that you're going to learn are things like adding and subtracting vectors graphically, or finding the component of a vector along a certain direction graphically. And so what I want to do in this video is make it clear exactly what's being referred to as a graphical vector, or the idea of what you're doing something graphically with vectors. Okay, so anytime you're doing something with vectors graphically, what's being referred to is the graphical representation of a vector. So an arrow on a page. Okay, this is a graphical representation of a vector. Now you could come up with other types of graphical representations, but this is the standard, most commonly, by far most commonly used graphical representation for a vector. And so again, if you're learning how to add and subtract vectors graphically, then you're going to be doing it with arrows. You're going to be looking at the idea of adding and subtracting vectors from the perspective of arrows like this. Even though, as we've talked about, an arrow is not a vector. An arrow like this is not a literal, actual vector. If you go on the road right now, there are vehicles all over the place that have vectors associated with them. They're moving with velocity vectors. They're moving with certain speeds in certain directions. You don't see arrows floating around outside. A vector is not an arrow, okay? So, but again, if you're learning how to add and subtract vectors, or you're learning how to find the component of a vector along a certain direction graphically, you're learning how to do all this graphically, then you're doing this with arrows like this graphical representation for a vector. Now, when I was first learning vectors, anytime it was stated that we were doing something graphically with vectors, I always thought that what was being referred to is, so there's two ways we represent vectors graphically. The most common way, the way you'll use the vast majority of the time, is it's going to be relative to a coordinate system. You're going to have a coordinate system, and then the vector will have a certain length and direction in that coordinate system. It'll have its vector space, length and direction, with the tail fixed at the origin, but then the arrow will also kind of have its own length relative to the master coordinate system. Okay, however, there's another way that will sometimes be used, and that's when, so you don't have a coordinate system, but instead a scale is provided in one of the corners of the page or the image. So you'll have something like this. So this vector here, and it gives a scale like this. Okay, so this is 0, 1, 2. Okay, so let's say this is a velocity vector, and this is meters per second. Okay, and what this is referring to is this length on the page is 1 meter per second. And so what the idea is, you come to the vector and get its length, so that's about 4, and then you come here, its length on the page. Okay, so this vector magnitude then is about 5.4 meters per second. Okay, now again, graphical vectors aren't commonly done this way, but you do sometimes see this. And the reason why I thought that this was only what was being referred to when it came to graphical vectors, or doing things with vectors graphically, etc., was because what you can see is that for this setup here, you have to draw the vector to scale, or else it's not going to work. If you don't draw the vector to scale, then you have no idea what the magnitude of the vector is. Okay, and so, but with that then, if you're going to be learning how to add and subtract vectors graphically, or do anything with vectors graphically, the vectors are going to have to be drawn to scale, or else it's kind of pointless, right? That's the whole idea. And in my mind, I was so used to, so, you know, if you're in physics or engineering and you're doing a homework problem, a big homework problem set, what we normally do as students is, so if we're going to be drawing a coordinate system with a vector in it, well, we've got our sheet of paper. We'll put, you know, an x-axis, a y-axis, as straight as we can. Maybe if we had a ruler, we would draw it with a straight edge. Then we'll just roughly put the tick marks as evenly spaced as we can. Okay, and so now if I've got the vector 2, -1, all right, well, in general, we can kind of pick any start point we want. So let's say we're starting here. Then you go 1, 2, -1, and there's the vector v. Okay, but this isn't drawn, as precisely as possible to scale, right? However, it's not that big of a deal that it's not drawn precisely to scale, as opposed to the previous method with the scale provided over here. And it's the reason why this is not that big of a deal is because the information as far as the components of this vector and the magnitude of this vector, it's all contained on the coordinate axis. I know that this is 2. This is 4. I know that this is -2 and this is -3. I can see what the components of this vector are. I could, if I wanted to calculate its magnitude, we haven't talked about calculating magnitudes yet, but I can see what these different positions correspond to. The information is on the coordinate system, as opposed to here that the information is contained within this scale. This has to be drawn to scale no matter what. Okay, and so in my mind, it was like, oh, okay, well, this isn't when you have vectors within a coordinate system, that's not graphical. However, that's not correct. Okay, and yes, if you're doing a homework problem and you're not going to be adding or doing stuff with vectors graphically, which most of the time you don't, then you don't have to draw things to scale. You've got the vector information here. If you want to add this to another vector, then you do it numerically, which we'll talk about in another video. You draw these vectors on roughly on the page, and if you want to add them or do anything between the vectors, you do it with these two vector matrices numerically. That's what we do most of the time. Okay. However, with that said, though, any vector on a page is graphical, and the way you want to think about that is this: if you were giving an official presentation, if you were writing a textbook or something, doing something official, okay, well, then you wouldn't draw a vector within a coordinate system rough like this. You would draw it to scale. You would use a straight edge to do the axes. You would evenly space the tick marks. You'd measure it off, right? You would, okay, we'll space each tick mark 1 unit here, or half a unit. You would do like this. You'd make the tick marks like that. And then you draw the vector in to scale. Right, so from that perspective, just remember, even a vector within a vector arrow within a coordinate system, that's graphical. So everything we're going to learn in the upcoming videos about adding, subtracting vectors graphically, the components of a vector along certain directions graphically, that applies to any vector arrow in any circumstance. Because from an official perspective, any vector arrow that's drawn in any circumstance is going to be drawn to scale. From an official, formal perspective, not the perspective of doing like a homework on some scratch paper. Okay, but now with that said, then, why are we learning how to do certain things graphically with vectors? Why don't we just learn how to add them numerically? Especially since we know vectors can be more than 3 dimensions, and we can't really draw a 3-dimensional vector arrow. Why are we even learning anything graphically with vectors like this? Well, the reason why this is done is just to try and provide us with some intuition behind what it means to add vectors. Because, when you get to linear algebra, we abstractly extend our thinking past 3D space, but we still kind of think of like these planes in 5 dimensions, 6 dimensions, vectors in 8, 9 dimensions, right? And so it can be useful to have this idea of, okay, when you're adding vectors as an arrow in 2D or 3D space, you can kind of abstractly extend that idea of adding vectors, in 8 or 9-dimensional vectors. It just gives us a sense for the meaning of adding vectors or subtracting vectors or doing anything with vectors. In the same way that the graphical representation of a vector just as in itself gives us a sense for the meaning of a vector, and that it's a quantity that has a magnitude and a direction. It's a good graphical illustration. Well, if anything that we can also, any kind of operation with vectors that we can illustrate graphically will just give us an intuition behind what it means to do something like this between vectors. Okay, but however, it's still extremely important, though, to keep in mind that anytime you're learning about operations on or between a vector graphically, always remember that an arrow is not a vector. Okay, I've talked about this before, but it's like, so we can use an equivalent idea of a graphical representation for a scalar. Okay, so you provide a scale in the same way. The diameter of these dots corresponds to a certain weight magnitude or a temperature magnitude, but these dots have no direction, right? So when we're learning how to, in elementary school, we're learning how to add and subtract numbers, which is what we do with scalars. We're just adding two numbers, right, or subtracting two numbers. Well, we're also trying to learn the intuition behind what it means to add and subtract. If I have 2 rocks and I have 3 rocks and I add them together, now I have 5 rocks, right? That's how we build our intuition behind what adding and subtracting means. Okay, well, we could also try and build our intuition behind what adding and subtracting means from a scalar standpoint. I'm going to add this temperature scalar to this weight scalar, and you just combine the 2 diameters of the dots, and you get this bigger diameter. This isn't the most intuitive way of looking at it. That's why you don't see this kind of a representation for a scalar. But vectors it's really intuitive. Okay, but we could look at that graphically, right, and try and get an intuition behind it. But it would be silly to start mixing up the idea of this graphical representation with an actual scalar, an actual weight or temperature, and the idea of adding a temperature and a weight, or adding 2 weights or something, right? So like you add 50 degrees Fahrenheit to 50 pounds, you get 100, whatever that would, I don't know what the units that would be, but that would be Fahrenheit plus pounds. But I guess it would be better to say we're adding 2 weights or 2 temperatures. But to start mixing in the idea of saying, okay, well, what if the weight, what if you don't have where does the weight dot have to be? Does it have to be at the center of the temperature dot? Can they be off-centered a little bit, and can you still add them? That's being silly, right? There is no temperature dot. There is no weight dot. We're just adding 2 numbers, right? When you add 2 temperatures together, it's kind of like the temperatures are going to combine. Maybe. It depends on the physics of the problem. Maybe you need to multiply that. I don't know. I guess if you have 2 people on a scale, then you add their weights, and that's going to be the weight on the scale of the sum of those 2 people's weights. But we're not going to start mixing in, acting like these graphical representations for weights and for scalars are actual scalars, the actual physical phenomena. Okay, and it's the same idea. If you have vector v1 and vector v2, and we're going to look at the idea of adding vectors from a graphical perspective, well, that's just to build our intuition behind what it means to add vectors. But don't start confusing yourself with thinking, oh, well, treating the vectors like these arrows like they're actually vectors. We're just using this graphical illustration to help build our intuition behind what it means to add vector quantities. With vector quantities being just as simple as scalar quantities, except, well, close to as simple. They just have a little bit more complexity. They have a direction in addition to a magnitude. But other than that, they're just quantities that you can add, subtract, multiply.